Welcome back. Another lesson. I like this one a lot. I'm going to be honest with you. Some people kind of give this one short shrift in calculus, but it is so important. It is so useful out in the world. It is old, but still gets used a lot. So Newton's method. I called it getting to the root of the unknowable. It turns out many problems in math are either we can't get exact answers for, like we actually cannot, or it's just too expensive. It takes too much time, too much processor time, or it's not worth the time. And so estimating is still incredibly valuable, and having automated ways of estimating is very valuable. And you see this all the time because your calculator gives you decimal approximations to things like pi. It's not exactly pi, it's approximating it. So you are using approximations all the time. Those approximations only have a couple of ways to be found out in the big world, and Newton's method is one of the biggies. So I think it's worth caring about. To get to know what is Newton's method, we need to remind ourselves of what is a root. So x naught is a root of some function f if, when I plug in x naught, I get 0. That's it. So you are probably used to finding roots of polynomials. Where is that polynomial 0? Why do we care about roots? Well, there's many reasons, but here's a good one. If I want to solve some big nasty equation like this one here, any equation, solving it, I can turn into the question of finding a root. So if I just rewrite it by bringing everything to one side, e to the x plus tan of x minus 12x squared plus e to the 5x plus 1 equals 0. The second I write all that stuff equals 0, I've turned this question into one of finding a root. What is the root of this thing on the left? So if I can get good at finding roots, I can solve just about anything I want. Okay, and that's what Newton's method is good for. In this particular situation, can I find where something equals 0? There's maybe a different way I could phrase questions that look like this. Where do y equals x to the 5th and y equals x minus 1 cross? And if I wanted to find where those two curves cross, it would really just be a matter of saying, all right, well, when does x to the 5th equal x minus 1? And that's going to happen exactly when x to the 5th minus x plus 1 equals 0. And if you want a challenge right now, see if you can figure out where those cross or what number it is. It is a lot harder than you might think at first. Okay, so why do I need calculus to do algebra? Right? Why is this necessary? Like even that problem above, x to the 5th minus x plus 1, seems like I should be able to have some other way to do it. And what you might not realize is that chances are the nastiness of numbers and polynomials has kind of been hidden from you. So it is not obvious at all how to solve this equation. So we could consider the function, the polynomial function, f of x equals x to the 5th minus x plus 1. And I could ask, where are the roots? Where is it 0? And I could even ask, does it have a 0? One way I could show it has a 0 is by saying, oh wait, at -1, this thing is just -1 plus 1 plus 1. That is equal to 1. Notice that -1 to the 5th is in fact -1. Okay, and at -2, this thing becomes, it looks like -2 to the 5th is -32. Plus 2 plus 1 is equal to -29. Okay, now you're asking, Austin, why do I care that this is 1 and -29? It's because we have the intermediate value theorem. Because x to the 5th minus x plus 1 is continuous, because it's continuous, why is it continuous? It's a polynomial, so it must be continuous. It's continuous, it hits up a negative number and it hits up a positive number, so somewhere in between it must be 0. Somewhere in between -1 and -2, it must be 0. So it must have a root. In fact, I graphed it over here. Whoop. And you can kind of see somewhere in between -1 and -2, this polynomial is in fact 0. It has exactly one root. Now, here's the other fun fact about this particular root. It is famous. This polynomial has a name. It's called the Obel-Ruffini polynomial. And you cannot find this root. Can't be done. We can only approximate it. And this should be a little bit mind-blowing. they proved this. This is a really big deal in math and algebra. That the proof looks a little bit like this, or rather, it sounds a little bit like this. It says, hey, we have a quadratic formula for solving quadratic polynomials, things that have an x squared, and we have one for x cubed. It looks really nasty. That's a cubic formula. We even have a quartic formula, which looks more like a flowchart. It usually takes up about a page to write down. It's really awful. But there, in fact, does not exist a quintic. There is no formula for solving degree 5 polynomials. Some of them you can solve, but there is no general or universal one. The reason is that the root of this polynomial and other ones like it cannot be written as some combination of addition, subtraction, multiplication, division, powers, and roots. There isn't a nice way of writing it. And if there is no nice way of writing it as some combination of all those functions of whole numbers, then there couldn't possibly be a formula for it, which is pretty incredible. So there cannot be a quintic formula for degree 5, and there is no nice way of writing this number. Root cannot be written nicely, but it does exist. All right, just like pi exists, but there is no other nice way of writing pi. If there was, we wouldn't need that symbol pi. We would just write 22/7. If there's a nice way of writing e, we wouldn't use the number e. It's just some kind of infinite decimal, and all we can really do to get a handle on it is approximate it. Okay, that was a long sidestep there, but I think it is worth knowing at this point in your career that this big wide world of numbers and solutions and roots exists. So let's give it a try. We're going to do a linearization. This is what we just learned. A linearization, and we're going to go based at -1. So we are going to try to take a tangent line and do an approximation. So this is a poor drawing up here. Here's my tangent line. I'm going to try to ask, where does that tangent line approximation cross 0? And that should be pretty darn close to the right answer. So my linearization, L of x at -1. Well, I know what my f is. My f prime of x, polynomials go pretty fast. 5x minus 1. Great. So f at -1, we already know, is 1. F prime at -1 is equal to, looks like just -6. Okay, so do we know our linearizations by now? Let's give this a try. We're going to start at our value of -1, that y value, and then we're going to add on my slope times x minus my a value, so plus 1. In other words, this is -1 minus 6x plus 1. Great. That's my linearization. The approximation to my root is just going to be, where is that thing 0? Because it's a line, I can solve for this very quickly. This looks like 1 equals -6x plus 1. So -1/6 equals x plus 1. Almost there. X is equal to -7/6. Not a bad approximation. All right. So this is not our final solution, but to understand how Newton's method works at its core is we ask ourselves, where's a good place to start? A is -1, someplace close. We consider the linearization, and then we ask, where is the linearization equal to 0? And that should, hopefully, get closer and closer to the correct root. Closer and closer is a little bit leading. Let's see what we mean by that. Well, we got this new approximation of -7/6, which hopefully is a little bit better than what we started at, -1. So now, why not just keep going? Why not start at -7/6? Okay, and in fact, let's go ahead and just keep good with our notation. Let's write when a equals -7/6 to keep with our linearization notation. So we could then play this whole game again and say, all right, in this case, f of -7/6 equals, and we could say f prime of -7/6 equals, and we could build L of x again. I'm intentionally doing this a little bit abstract for you. Okay, that would be my linearization, whatever those numbers are in there. And then I would ask, where is that equal to 0? And I would solve for x. And I would get a new value that I could plug in again. So because each time I solve for x, I get a closer point, I could make that my new base, and I could do this linearization again. So I intentionally left that a little bit abstract with all those functions in there because I want to write this down sort of the way we're going to do it, which is to mechanize this process of finding a linearization and solving for 0. So what do we need here? We need an f. We need an f prime. We need a good place to start, some x1, and we need a way to know when to stop. So in fact, let's go ahead and go back up here for a second. Let's see if I can't formalize this a little bit. If I wanted to know when is L of x equal to 0, well, that's just saying when is 0 equal to f of a minus f prime of a times x minus a. Now, if I were to solve that, I would get something that looks like x equals a minus f of a over f prime of a. Okay, just solving for x. Oops. But I don't want to use an a here. What I want to do is each time I want to plug in my last x. So here is my Newton's method. I've got an f. I've got an f prime. I've got some good place to start, x1. Way back up here we started at negative 1. And we'll have a reason to stop. So what I'm going to do is I'm going to start at my x1, that was my a, and I'm going to plug it in to this fun formula, x1 minus f of x1 over f prime of x1, which is exactly what you get if you take the linearization and you set it equal to 0. Okay, just written out with x1s instead of a's. Whatever comes out of that, whatever comes out of this, the root of my linearization, that's going to be my x2. That's my next approximation. Okay, and then I'm going to repeat. I'm going to take this x2, let's do my xi, I'm going to plug it back into this formula, and I'm going to get an x3. I'm going to take that, I'm going to plug it into this formula to get an x4. And so on until you stop. And usually stopping means we did the number of iterations that we wanted. We picked how many iterations. Sometimes it means that I'm keeping track of 4 decimal places and it stopped changing. So we're stable up to 4 decimal places. It can mean that too. All right, let me just draw a quick picture on the side because I think it helps to see this a couple of times in a couple of ways. If I had some curve and I said I'm trying to find a root and I start at this point right here and I take the tangent line. I say, where is the tangent line 0? Right there. Great. So my x1 would be here. My x2, change color, my x2 would be right here. From there, I'm going to do a linearization again from that x2. Whoop. Say, where is that 0? And that is going to give me some x3. And we just keep repeating and repeating. So we take a tangent line, base at a point, we solve for where it's 0. That gives us the base of our next tangent line. We say, where is that 0? That gives us the base of our next tangent line. And hopefully this should get closer and closer to the real root. Certainly play around with this to get a good view of what it looks like. It is surprisingly effective. Like it is more effective than it has any right to be. All right, let's see what this looks like in action. I want to estimate the 6th root of 2. So if I want to estimate the 6th root of 2, well, I need to write some function whose root is the 6th root of 2. Let's see what that might look like. If I had x is equal to the 6th root of 2, that might look like x to the 6th is equal to 2. In other words, x to the 6th minus 2 is equal to 0. Okay, beautiful. So my f is x to the 6th minus 2. All right, so sometimes you have to massage a little bit to phrase a question in a way that looks like finding a root. 6th root of 2 isn't a particularly nice number, but we can estimate it. In fact, under the hood, many of your calculators are doing this to get good estimates, or something like this. Let's go ahead and see what we get. We need a good place to start for this, and so we need to pick a number that seems, I don't know, kind of close to the 6th root of 2. So sometimes this will be given to you, sometimes you just kind of need to know, but try to play along with this if you can. I'm going to start at 1, because it is fairly close to 1. Okay, if I plug 1 into x to the 6th minus 2, I'll do this longhand this first time. 1 to the 6th minus 2 is equal to -1. Okay, its derivative, maybe I should have written this down up here, always a good idea. F of x is equal to x to the 6th minus 2. F prime of x is equal to 6x to the 5. So its derivative, when I plug in a 1, I would get 6 times 1 to the 5th is just 6th. Now I plug all this into here, and if I do this right, I would get 1 minus -1 over 6. So 1 plus 1/6. And I'm going to go ahead and write this as a decimal. I think this is an approximation method. It is okay to keep decimals around. So 1 plus 1/6 is about 1.6667. As many sixes as you want. Okay, so now this number becomes my x2. Oops, 1.1666. As many sixes as you want, 7. Now I need to plug that into my f. I need to plug it into my f prime. So I'm going to do this in real time. Hopefully you are playing along. See if you can do this with me while we plug these into our appropriate functions. So I'm going to plug in 1.16667 to the 6th minus 2. And I get, looks like 0.52. I got to make a choice here. Let's go with 4 decimal places. Always carry around at least one more than you think you need. Now I'm going to plug in 1.1667 into that derivative. So I get 6 times 1.6667 to the 5th is 77.168. Okay, much bigger. Next up, we need to take x2, this 1.1667, minus all these together, and we should get something a little bit smaller than 1.667, and we do. We get 1.12644. There we go. Great. We're going to do this again to find, or rather, this number becomes our x3. I'm going to do one more row with you, and then I'm going to do the last row to you. So I plug that into f, and I get 1.1264 to the 6 minus 2, and I get 0.0424, and then I take 6 times 1.1264 to the 5th, and I get 10.88. You don't have to do this whole table. I just think it's kind of helpful in showing my work for you all. Certainly it would help you keep your work a little organized for yourself if you did. I want one more decimal place here. 879, so 880. 8796, that sounds better. And I plug all that in, and I should get, looks like 1.1 where'd it go? 1.1225. All right, you notice that the changes in between these get smaller and smaller and smaller each time. Okay, so eventually it should stabilize. This number comes down here. This is my x4. Okay, so you have to know when to stop. If you wanted to keep on going down to x5, I'll write it down here for you real quick just to check your own work. x5 should be 1.1225. And then x6 would actually be 1.1225 also. So it does stabilize after a while. If you carry another decimal point, it goes a little bit further. Okay. So one stopping condition would be when do my numbers start to stabilize like this. Another would be, hey, just go to the fourth step. Okay, that is a bit of work to do by hand. I think it's important to do a couple by hand, and then I think it's important to realize that this is amazing partially because it's great computer work. So we'll talk more about doing this via computer in just a little bit.